Okay, let's resume. So in the last 35 minutes, I want to finish this and give you some example. So this KKT, so this is called Karush-Kuhn-Tucker. It's a necessary condition for the original optimization problem that can be non-convex. So if I have this optimization problem here that is non-convex, my KKT gives you necessary condition for local optimality, local optimum solution. But interestingly, when the problem is convex, this is not only necessary, is also sufficient. So what it says is the following. You have essentially 5 conditions to satisfy. The first 2 is the primal feasibility. So you just say you have to satisfy the constraints. And we had 2 constraints. We had the inequality constraint and the equality constraint. So obviously, to be local optimum, you have to satisfy the constraint, right? Otherwise, you're not feasible. Dual feasibility, this lambda has to be positive. This is what we saw already. And the idea there behind is, again, that the Lagrangian, if your lambda is positive and your x is feasible, then essentially this term will be negative and will decrease this term. So you will act as actually you will obtain a dual function that is a lower bound. So that's the idea. This one has to be positive. It has to counteract the effect of Fi essentially. So this is needed. And then we have the other 2 constraints. Says the first one, this is called complementary slackness. Your lambda multiplied by your f, so this is your inequality constraint. Your lambda has to be always positive or equal to 0, but additionally your lambda is such that this product has to be equal to 0. So what that means is, it means that you cannot have lambda and Fi at your optimal point that are simultaneously positive. This would not work. Or you cannot have this one being positive and this one being negative. So typically what you have here is that your lambda is equal to 0 and your f of x is non-zero, or if your Fi of x is equal to 0 and your lambda is non-zero. So those typical events that you get. And there is a very nice interpretation of this I will show you in a minute. And the last one is the typical stationarity that you have when you have unconstrained problems. So typically when you have unconstrained problem, what you do is that you just take a derivative, and when your derivative is equal to 0, you know that you can have a local optimum, right? This is the example I have here. I have an unconstrained problem. I take my derivative. I find 2 points where actually the derivative is equal to 0. This is a necessary condition for local optimum, right? So what you have here is a generalization of the stationarity that we had in the unconstrained problem, but now generalized to the case where we have constraint problem, essentially. And so if you remove the constraints, you end up with just this, with the Lagrangian becomes the objective function, f naught. And so you end up with all those constraints becomes the classical stationarity condition that you have in unconstrained problem. Right, so this is very useful. Even if you have a non-convex problem, this KKT is necessary for global optimality, but is not necessarily sufficient for global optimality, right? But it's necessary. But when it's convex, those conditions are not only necessary, they're also sufficient. So if you find a point that satisfies those conditions, and your problem is in convex, you know that actually this will be global optimal. Right? But if your problem is non-convex, and you solve this problem, you say, well, yeah, it may be a local optimum, but I cannot guarantee that actually this is the global optimum. It's needed for global optimality, but it's not sufficient. Right, so let's try to interpret this a little bit. So we have this Lagrangian, this Lagrangian function plus plus those constraints, right? And so I was saying earlier that Fi and Hj, they're actually kind of very hard constraints because you really have to satisfy them in the original optimization problem. But in the Lagrangian, they're replaced by soft version. You don't impose Fi or Hj to be equal to 0 per se in your formulation. But you replace it by soft version where essentially your constraints are replaced by kind of a price that you pay if you don't satisfy those constraints. So for instance here, if your lambda is positive, right? If your lambda is positive and you don't satisfy this constraint, this becomes positive, then you pay a price, your objective function suddenly increases. And it will be increasing even faster as your lambda gets bigger, right? So your lambda will tell you a little bit what is the price that you pay by not satisfying those constraints, right? How quickly you will actually deviate from your objective function by not satisfying the constraint. So this is the idea behind this lambda. So it's also, people call it displeasure. So if you really violate this constraint, then your Lagrangian will grow very quickly, will become much bigger than your original objective function. So this will, you pay a price for not satisfying the constraint, essentially. That's what it says. Right, so the complementarity slackness is the following. If you satisfy the constraint, so if your optimal point here satisfies the constraint, then the complementarity slackness says that, so you satisfy strictly. So what that means is that at the optimal point, you're not even equal to 0, you're strictly smaller than 0, right? So this means that your inequality constraint is actually inactive in the sense that you're not even at the border of the inequality constraint. So for instance, if you have a point here and you have a constraint that your point has to be smaller than the values of x, I don't know, that is there, your constraint may, for instance, would not be even satisfied, right? Or would be satisfied. So here, your constraint will be strictly satisfied. You're not even on the boundary conditions where f of x is equal to 0. And so what that means is that you could loosen your constraint a little bit, and you could say, well, if I made this constraint a little bit tighter by saying I will replace fi of x, instead of being equal to 0, I will say fi of x has to be smaller than minus epsilon, with epsilon positive. I make a little bit more constraints. Well, what that says is that this will not affect so much your objective value, because your optimal point has been achieved with a constraint that is inactive. So even if you tighten that constraint a little bit, you can expect that your objective value, your P star, will not change much, right? And that's the reason why when your constraints are inactive, so this is clearly smaller than 0, by the complementarity slackness here, this product has to be equal to 0. If this is strictly negative, this lambda I has to be equal to 0. Lambda I is the price you pay by not satisfying the constraint. So because you satisfy the constraint very strictly, you don't really pay a price if you actually tighten it a little bit more. That's what it says. And then you have the opposite that say if you have an active constraint. So if you have the optimality, you actually have your constraint is really active, then that says that, well, your lambda will have to be non-zero, strictly larger than 0. And if your lambda is small, well, it will have, if you change the constraint a little bit, if you tighten the constraint a little bit, it will have little influence on P star. But if lambda is large, it will have great influence on P star. So your Lagrangian multiplier is a measure of the sensitivity of your objective function to any change in the constraint, essentially. That's what it It's a measure. How much your constraint can be tightened or loosened. If your lambda I is very large, it means actually you're very sensitive to any change into those constraints. Right, so let's go back to the example I gave you. So this is my linear problem. I wrote the Lagrangian, and then I can write the KKT, those 5 conditions. And from those KKT, you can obtain the optimal point. And that corresponds to the point we just computed before using the dual function, right? So you can do this at home, is a good exercise. I will not spend time on this one. But the one I want to spend a bit more time on is this water filling. So this is already a solution that you're aware of. We have seen this already. It's very common in communication. And so let's write this problem again. So I have a sum of rate where the lambda k here in the MIMO case would be the eigenvalues of this channel matrix, and sk would be the power allocation that I allocate to these k eigenvalues, right? And I have a sum over those lots because I'm transmitting essentially over multiple virtual paths, and each of them is allocated in a certain power level, right? And those virtual paths are really non-interfering with each other in my MIMO channels. My power allocation is non-negative, and I have a sum power constraint. So I want to allocate all my power, but the question is how to allocate the power across those k subchannels, right? So we know the solution that you will allocate more power typically to, so sk will be larger if lambda k is large, and sk will be smaller for the lambda k is smaller. And we know exactly how to do that, but the solution of this comes from just looking at the Lagrangian. So you can write your Lagrangian, which is the objective function, minus here you have a equality constraint, right? So sk is larger than 0 or minus sk is smaller than 0. So I have minus sk multiplied by, this was my lambda that I had before. And then I have an equality constraint here on the power, right? And now what you can do, you can take the Lagrangian of this, you can take the KKT conditions. So you can write your KKT conditions for this, and this would give you the necessary condition for global optimality, but because it's a convex problem, actually this can be shown to be actually necessary and sufficient. So if you find a point that satisfies the KKT conditions, then you're done. You know that you have a solution for this problem. And this is what you can do here. Those are the 5 KKT conditions. So the first one is feasibility. Power allocation has to be positive. Not an issue, we know that. Some power constraint has to be satisfied. Those are the 2 constraints, right? The Lagrangian multiplier attached with the inequality constraint has to be positive. This comes from the dual feasibility. Complementary slackness. So my lambda that I had before multiplied by inequality here has to be equal to 0, right? So if this one is positive and this one is equal to 0, or if this one is 0 and this one is positive, right? This is the typical scenario that you have. And then last one is this derivative, essentially, that is equal to 0, so the stationarity. So you take the derivative of the Lagrangian with respect to your your optimization variables here, and this has to be equal to 0. And so you end up with 5 equations, and from those 5 equations, you can write 2 of them that are actually very meaningful. So this one, we know this is positive, right? So if you bring this on this side, this term has to be positive. And so essentially, you're going to have V has to be larger than this, because this is positive, so this is what you have here. And you have also the condition that this chi here, or I don't know how to call this, if you bring to the other side, this is to be equal to V minus this, and you plug this into this, so you're going to have this is the same as this, multiplied by sk has to be equal to 0. So you have 2 conditions. And now what is interesting is that from this, you can figure out what needs to happen to SK. And so you can say first, well, what if my Lagrangian multiplier here, what happens if it's smaller or larger than this numerator here, right? So if it is smaller, if it is smaller than this numerator or larger, then you have those two conditions here. So let's start with the smaller case. So your nu is smaller than this quantity. So if this nu is smaller than this quantity, this is possible. So you're going to have Sk that is positive. If nu is smaller than this numerator, you're going to have an Sk that is positive. So this nu is smaller than this. So you're going to have an Sk that is positive only if this condition is satisfied. So you have Sk is positive, and you have from the other conditions, then this term has to be, the nu has to be equal to this. So here, sub. So if nu is smaller than this, then you have nu here is smaller than the numerator, right? If this is smaller than the numerator, sorry, I'm lost here. So if nu is smaller than the numerator, so if your Sk is positive, then you need to have 84 that this have to be equal to this, right? Oops. So this smaller than Nq will work only if Sk is positive. And if Sk is positive, right, if Sk is positive, it means actually this term has to be equal to 0 because of the complementarity slackness, right? So this one is smaller than this, okay, but to have Sk positive, then if this term is positive, then this term has to be equal to 0. That's what it says. And if this term is equal to 0, then you can find your Sk as a function of your nu. Right? And this is the solution that we had earlier in the module. This was our water level, and this was 1 over the SNR. So if your lambda is large, you actually allocate more power to Sk. That's what it meant. Right? So it really comes here, and you can do the same if your nu does not satisfy this, then you can show that your Sk has to be equal to 0, essentially. So you have two cases. One case where your Sk is non-zero, one case where your Sk is equal to 0. When your Sk is non-zero, you really see that you allocate more power whenever your channels is stronger, when your eigenvalues are stronger. And so you end up with exactly the solution that I had earlier on. And your multiplier here, your water level that we talked about, is essentially related to Lagrangian multiplier that needs to be computed such that you satisfy these constraints. Right? So this is just an example of how you can use KKT to really find closed form solution for some optimization problem. And because this is a convex problem, you find a solution that satisfies the KKT, you know that actually this is the global optimum solutions. Right? The problem is actually it's not always easy to formulate those KKT conditions, and it's not always obvious to actually solve this in closed forms, right? So for some problem it works, for some other problem it does not really work. So I will show you another examples where actually it's useful to do KKT to find the global, not the global optimal solution, but actually no global optimal solution, but just a structure of it. And this was this power minimization subject to SINR constraints. Okay, so now at least with this, you see where this comes from by applying those KKT conditions. And there are other examples that you can look at. So this is this example of wireless power transfer where also you can use KKT here in this case in some simple scenarios. You can find global optimum solution in closed form as well In general, it's actually a GP problem, so it's not even a GP. It's actually a non-convex problem that you can approximate as a GP, but for some very specific setting, you can use KKT and you can get some insight. But I will skip this for the time being. Right, so the last, I will come back to this example one that we had earlier on that we solved using SOCP and SDP. And I want now to look at KKT to resolve this problem. So the problem we had is this power minimization subject to SINR constraints, right? And we were transforming this into an SOCP using CVX. We were transforming this into an SDP using CVX. Now let's look at the Lagrangian of this, and let's apply KKT conditions, right? And we can always do this, whether the problem is convex or non-convex, it does not matter, right? Now, what is interesting in this case is that you can really find a nice structure of the optimal precoders, and that gives you some really nice insight, which you wouldn't get from this SOCP and from the SDP. So what is the Lagrangian? Is this objective function. This is my F naught there. And I have now K constraints, right, that I'm writing here. So each of those constraints is allocated Lagrangian multiplier lambda K. And this is essentially this constraint that has been rewritten. So typically you write something that is smaller than something. So this is what we have here. This is typically a negative constraint. And so this is my objective function, this is my constraint, and this is my Lagrangian multiplier. And one of the conditions in the KKT is a stationarity, which means I take this Lagrangian and I take a derivative with respect to those objective optimization variable W, and I want this to be equal to 0. And so you can do this, you can do vector differentiation, and so you have here some solution. This comes from some well-known tables, but the baseline is that if you take this and you equal this to 0, you end up with a relationship now that really gives you some interesting insight into the structure of this WK. And now you see that here you have a function that is function of WK here, WK there, and WK there. Right, so you can extract your WK, and you can find some interesting solution that really satisfy this problem. And so this is what we have. This is what we have here. So I have here. I take this term and I equate this to this term essentially. So this term goes to the other side, right? So I don't do much here. This is what I have here. And I will give you two solutions to that when we add the red terms and when we don't. So when we add the red terms, we have this solution. When we don't add the red terms, we have these solutions. So if you add the red terms, essentially I add this term here and the same term there. I don't change anything. It's just the same term on the left and the right. But by doing this, you see I have a sum over I different than k of those HIWK. And here I have just HKWK. So now those two together would give me just a sum over all values of I. They don't have to be different from K. This is what I have here. So what you have is that you have a WK here, you have a WK there, and you have WK there. So you have this term here. After you remove your WK, you take this ahead here. You have this inverse of a matrix that comes from the inverse of this matrix here. And the right side here is this term and these terms are the same. So this comes out here and the HK, and this is just a scalar that is coming from this plus this. Right? Now what is interesting here is that this tells you that the structure of my precoder actually needs to be something like this. Now this looks a bit complicated because you have WK there and WK there, right? But the insight is the following. This is a scalar. And this is a scalar. So this whole term here is a scalar. So you can just say, okay, let's imagine this is a scalar. This is a vector. And so I have a scalar multiplied by something that is a vector. I have here my H. So this is a bit like my maximum ratio transmission. And then I have a matrix that performs some kind of rotation. So if this term here is very small, I have only the identity matrix, and I have my precoder is roughly aligned with HK, multiplied by some scalar, but primarily aligned with HK. So this is like some maximum ratio transmission. But if the interference here is not negligible, then I need to rotate away from HK. And that's the intuition, right? So this is very useful. And this scalar, you could view this, we'll look at this in a moment. But this is, you see, this is quite interesting. And so if you don't have the red terms, essentially you have a sum where actually you have I different than K. So both solutions are the same, are equivalent, but they're just written differently. One where you have a sum over K, one where you have a sum over non-K. So here you have essentially, this is a bit reminiscent of what we have in the MMSE receiver. You're looking at the precoder for user K, and you see the interference from all the other users different than K. Remember in the MMSE receiver, I gave you multiple alternatives way of writing it, right? And we had option 1 and option 2. And option 1 was like a function of all the terms, the interference plus the intended signals. This is what we have here. I have the user K channel and also all the interference. And here I have the other alternative where I have all the interference only. I don't have the intended signal. So you can really relate this a little bit to the MMSE receiver that we looked at, even though this is a transmitter side, but there's some similarities between those two expressions. So this is not per se not exactly MMSE, but you see that actually the term that we had in the MMSE here is actually a function of your Lagrangian multiplier. So depending on how you choose your Lagrangian multiplier, you can actually influence how much you want to rotate away from your MRT precoder. And the choice of this lambda will be a function of your constraint. Right. So another way of writing this is the following. I say, well, now I have a structure. This is going to be my direction. Well, it has to be along this direction. So I can say my precoder will be this one divided by its norm. That should be its direction. And then I can allocate some power. And this is what I'm writing here. I have this one, that's the main term I had in the previous slide, divided by its norm. So this will be the directions of the optimal precoder, and then I'm allocating some power. And if you compare this one with this one here, you must have some relationship between the scalar term here and this power allocation pk. And this is what is written here. So this term here, this norm here multiplied by pk, should essentially be related to the scalar term here. Right? And so this gives me some relationship here. Once I have my W that has been fixed, I can then compute my power allocation. So I have my power allocation, the beamforming power if we want, and then I have the direction in my precoder. Right? So I split it into two. And then the last thing you need to compute is, you see all those terms are function of the Lagrangian multiplier. So your precoder is a function of the directions. The direction will be given by this term. That's your W bar. Will be a function of your power, which will be a solution of this equation here. So the pk will be a solution of this. But all this is a function of lambda I. So you have lambda I and lambda I here. So you need to find the solution of lambda I. And so to do that, you end up with an equation here. This is the solution of the power allocation. So the power allocation is actually obtained from those relationships. I will not go into the details, but you can have a look at this at home. So essentially, you can write the power allocation as a function of a matrix, and you end up with actually k equations and k unknown. That enables you to compute this power allocation to those k precoders. And this leverage the fact that at the optimal solution is obtained with equality. So the SINR constraints actually are obtained with, so the optimal solution is obtained when you have equality constraints on the, equality on the SINR constraints, essentially. So instead of being strictly smaller, it will be equal. So you can show that indeed, at the optimal solution, those inequality constraints should become equality constraints if you want to make the best use of the transmit power. And then you have a last solution, but unfortunately I don't have the time to go into all those details. But to find the Lagrangian multiplier, and here you have, on the left side you have WK, on the right side you also have W here, K. So you have a fixed point iterations, you fix your double lambda I. From this, you find your new lambda, you take the new one, you plug into the right terms, you find a new one on the left side, and you keep iterating. So what this gives you, just to summarize, is essentially using KKT condition to find optimal structure of your precoders, and that means you have an optimal directions, you have a power allocation for that precoders, and you end up with your KKT, your Lagrangian multipliers. What is in closed form? This power allocation is in closed form. This one is also in closed form. Your precoder direction is in closed form, but your lambda, you don't have really closed form solution from this. You need to find through numerical evaluations using fixed points. So it's almost semi-closed form. And if you do that, and this is something you're going to have to do in your coursework 3, you're going to have to come back to this example exactly. You can show that if you do SOCP or SDR for this power minimization problem, or if you do KKT, and KKT using the two solutions I gave you here, whether you add these red terms or not, you actually end up with exactly the same solution. So you have 3 different ways of actually solving the same problem, but the KKT has the additional benefit that you have some insight into the optimal structure, right? And you really see what's happening from this expression here, which is very insightful. You really start from your MRT and you rotate according to how much you have to deal with this term here. If this term is negligible compared to the identity matrix, essentially you do something along the channels of your intended user. And so one way to represent this is the following. You can have your HK, this is your channel directions. You can have your zero forcing beamforming would be actually another directions that try to really get rid of the interference. And then you can be something in between, that's your optimal beamforming directions, that will be somewhere in between here, that will capture a little bit of the MRT, a little bit of the rotation, but that will be somewhere in between the zero forcing and the MRT, right? So I will not have time to go into more of those details, even though I would have liked to, but this is a little bit the insight that you're going to see. And this is very useful, because now you could, even if you don't have, complex software to solve your problem, you already know that that should be the structure of your precoder, and you could maybe just, design a nice Lagrangian multiplier that in practice work well, for instance, and that work well maybe for all conditions, for all propagation conditions, to simplify the complexity of the design. Right? So this is the case. So this was actually for the power minimization. You can do this for other objective functions, but these are a bit more complicated, for sum rate maximization, for instance. And you can show that the structure looks like this as well, but your choice of the lambda now is a bit different. But you always have this kind of insight. So you have an MRT and you have a rotation, and so you deviate a little bit from your MRT, and if you deviate even further, you end up with your zero forcing. So your optimal solution is a form of MMSE, right? If your interference is very dominant, this kind of disappears, and you end up with some form of zero forcing. If your interference here is negligible compared to this, you end up with some MRT. But in general, you end up with something that is in between. And your optimal solution is really a function of your lambda, which is your Lagrangian multiplier. Right? That's the insight that you get from this. So you will play with this in coursework 3 when you do power minimization. So you will get a bit more familiar with this. And I will stop here for today and for the module. The last example is not so important, is receive beamforming. It's related to one thing I mentioned at the beginning of the modules, where I said that you can use this matrix inversion lemma to demonstrate indeed the design of the precoder and the structure. If you're interested, you can see it here, but it's not something you will really need in your courseworks, but it's of useful interest. Obviously, there are many other things we could do in optimization. Advanced methods. And there are many things that you could do together with advanced communication systems on rate splitting multiple access. So this is one of the techniques that we pioneered in the past few years for very high efficiency and flexibility in communication system design and interference management. And this relies on very advanced optimization techniques. You can do this in massive MIMO, in intelligent surface, integrated sensing and communication on trust. You can use this in many, many different problems. And so very often in the research, you have this interplay between communication theoretic side that needs to drive meaningful communication schemes that are driven by, communication theoretic foundations. And the other side, you need to be able to optimize those schemes. So that's where the optimization comes in. Right? So I think I will